Welcome to this fascinating journey into the world of parasitology. Today, we are going to explore a creature that sounds like it belongs in a horror movie, but is actually a marvel of evolutionary biology, the vampire bat. We usually think of parasites as microscopic bugs or worms, but this highly evolved mammal proves that parasitism can take much larger, warm-blooded forms. Let us dive in and understand how this unique vertebrate survives. Now that we have introduced our topic, let us look at how this creature operates. Imagine you are fast asleep in a warm, dark barn. Completely unaware, a tiny, stealthy visitor lands softly nearby. Instead of hunting for meat or gathering fruit like most animals, this creature operates very much like a giant flying mosquito. It sneaks up to steal a tiny, painless sip of your blood while you dream. This is one of the rare examples in nature where a highly evolved mammal has adopted a parasitic lifestyle to survive. Understanding this creature shows us that parasitism is not just limited to microscopic bugs or worms, but includes complex vertebrates. Building on that fascinating introduction, we must now classify this creature scientifically. In parasitology, the vampire bat belongs to the subfamily Desmodontinae. It is classified as a temporary, obligate parasite. The term obligate is crucial here. It means the bat absolutely must consume blood to survive. This highly specialized diet is known scientifically as hematophagy. Unlike a tapeworm that lives permanently inside a host, the vampire bat is a temporary parasite because it only visits the host for a short meal and then leaves. Because it takes a small amount of tissue without immediately killing the host, it perfectly fits the definition of a micropredator. Knowing what it eats naturally leads us to ask how it manages to feed without waking the host. The vampire bat has evolved a highly specialized feeding toolkit. First, it uses specialized heat sensors located in its nose to detect warm blood vessels just beneath the host's skin. Once a spot is found, it uses razor-sharp teeth to make a precise, painless incision. But the most fascinating tool is in its saliva, which contains a powerful anticoagulant called draculin. This chemical prevents the blood from clotting, keeping the meal flowing smoothly while the bat feeds. To truly visualize this incredible feeding toolkit we just discussed, let us look at this cross-sectional diagram. On the screen, you can see the host's skin, divided into the upper epidermis and the lower dermis. Notice the superficial blood vessel running through the dermis, carrying the capillary blood flow. Above the skin, the vampire bat's head is positioned perfectly. You can see the sharp incisors, making that painless incision we talked about. Crucially, observe the draculin anticoagulant being introduced into the wound, allowing the bat to use its grooved tongue to lap up the continuously flowing blood. This diagram perfectly captures the mechanics of a temporary micropredator. Having seen how efficiently they feed, you might wonder why this matters so much to humans. The answer lies in the massive economic and public health impact these bats have as biological vectors for deadly diseases. Vampire bats are the primary transmitters of bovine rabies in Latin America. This transmission leads to the death of tens of thousands of livestock every single year, causing millions of dollars in severe agricultural losses that devastate farmers' livelihoods. Furthermore, as human populations expand into forested areas, these bats occasionally feed on humans, making them a direct public health threat that requires careful monitoring. To understand the true scale of this agricultural threat we just discussed, we must mathematically model the bat's daily blood consumption. Because blood is mostly water and low in calories, the bat must consume a massive amount relative to its size. This brings us to a simple, elegant formula. V equals M times F. Here, V represents the total volume of blood the bat must consume per day, measured in milliliters. The variable M is the body mass of the bat in grams. Finally, F is the feeding fraction, which is the percentage of its own body weight it must drink daily. Physically, this means if the bat's mass increases, the required blood volume increases significantly. If it fails to consume this volume, it can starve in less than 3 days. Now that we have our formula, let us apply it to a concrete example to see the daily burden of a single bat. We are given a typical common vampire bat with an average body mass of 40 grams. Biological studies show it must consume 50% of its body weight every night, so our feeding fraction is 0.50. We want to calculate the exact volume of blood it consumes. We choose our formula, V equals M times F, because it directly links mass to dietary needs. By substituting 40 for M and 0.50 for F, we calculate exactly half of the bat's body weight. The final answer is 20 milliliters of blood per night. While 20 milliliters, or about 4 teaspoons, seems small to us, it is a massive physiological burden for the host. Having calculated the burden of a single bat, let us scale this up to see the impact on a farmer's cattle herd. Imagine a local farmer has a herd targeted by an established colony of 50 vampire bats. From our previous calculation, we know each bat consumes 20 milliliters of blood per night. We need to find the total daily blood loss for the entire herd. To do this, we multiply the 50 bats in the colony by the 20 milliliters each bat drinks. This step aggregates the feeding behavior of the entire group into a single daily metric. The calculation yields a final answer of 1,000 milliliters. This means exactly 1 liter of blood is being drained from the herd every single night, which is a significant continuous fluid loss. With our daily herd loss established, we can now derive the true hidden cost of this parasite over a long period. This chunk of our derivation sets out to project the daily parasitic drain across an entire year of continuous feeding. We start with our known daily colony consumption of 1,000 milliliters. We know there are 365 days in a full calendar year. By setting up the multiplication of 1,000 by 365, we are assuming the colony size remains stable and feeds successfully every night. This mathematical reasoning allows us to scale up from a daily nuisance to a long-term agricultural impact. We will complete this calculation in the next step. Continuing from our setup, we now compute the final mathematical result of this annual burden. Multiplying 1,000 by 365 gives us 365,000 milliliters of blood over the course of the year. This is an enormous volume of biological fluid extracted purely to sustain the bat population. To make this number more intuitive for the farmer, we convert it to a standard larger unit by dividing our massive milliliter total by 1,000. This proves our final result. The colony consumes 365 liters of blood per year. This massive volume clearly demonstrates the intuition behind why vampire bat parasitism leads to severe anemia, secondary infections, and significant stress in livestock. To wrap up our lecture, let us review the most important ideas we have covered today. First, the vampire bat completely broadens our definition of parasitism. showing that a highly evolved, warm-blooded mammal can act as a temporary, obligate parasite. Second, we saw how its specialized physical traits, from heat sensors to the anticoagulant Draculin, make it a perfectly adapted micropredator. Finally, through our mathematical modeling, we proved the sheer volume of blood they extract, reinforcing their massive role as vectors for deadly diseases like rabies. You have now successfully covered the full topic of the vampire bat as a vertebrate parasite, understanding both its biology and its real-world impact.